This. So I'm going to talk to you about the lever rule. So when there's a rule, I think that this is something that is useful. And there's in the textbook, there's a whole chapter how the lever rule was derived. And I want to more focus on the essentially the use of the lever rule, not to the derivation of this. And also the tie line, what that means is the tie between a phase to the other. What that means is something that has a liquid phase and the vapor phase that are in equilibrium in this here. So in here, once again, I'm using the ZA to represent XA in the liquid and the vapor phase is the YA. And this is a example diagram, and then this is a 0, 1, so it all has this kind of diagram, and this is a 65 degrees C, this is 100 degrees C. So obviously this is an XA, and A is a higher boiling point. And A here is hexane, B here is heptane. Can you also see that already it's not ideal solution already? This is bothering me a lot, right? This is not, the Raoult's law doesn't work. Raoult's law only works in the region that when A is 100%, I guess this is the way the Raoult's law works. And maybe this is where the Raoult's law works. We are concerning about just the heptane as a solvent. Right? That's why I'm going to show you something that is different from the later on. What they call the azeotrope, which is the next section that I'm going to talk about. It's even more bizarre than this. But this has already become non-ideal solution throughout the composition. All we gotta do is, I just want to use this one to calculate what can I get. So the typical experiment that you will do is, you have a mixtures of hexane and heptane, and then you are going to fix you want to start with, you want to pass this portion, the composition. So this is where you are. So let me put it here. So you are right here. So at this temperature, which is higher boiling point than the heptane boiling point, but lower than hexane boiling point, somewhere in between. So you got this two, and then you know this is YA. This is an XA, which is this is a liquid, this is a vapor. Right? So that's a composition in between when your experiment at this designated at this temperature. And you're going to draw the tie line that is like a horizontal line, and this is your experiment point that you are at. And they want to give you the idea about the lever rule, which is you can do this, measure the length between your designated experiment point with the equilibrium vapor composition, literally using the ruler. Okay, so you use that, you measure that. This is to be, I don't know, 2 centimeters. Okay, I can do that, and then you go and you measure that the length between these two, and this is 6 centimeters, for example. So what it means is you bring it down, and then at this, if your experiment starting with this composition boil at that temperature, you are going to have gas phase, and their amount is proportional to the length of the other side. It is the same thing as when you do the seesaw. This is a length, and this is another length. Right? And the person here, you need a lot of heavier person, and this is a lot of lighter person there. Right? It's the same thing as here. What I'm talking about is the lever rule is about amount that you get versus composition. you're using this the level rules, and there's an equation for that. So I'm just give you this as a sort of the practical use. People write this one as a length scale, and this one is in the vapor phase, and this is the length scale in the liquid phase. Right? So this is starting from here. You go to the liquid, and that's the length, and you just literally measure the length, how many centimeters you have. And then this is what is called NV, N L, and that's what I call is a amount. Okay. So this one is just what L means a length here, and the lever rule as NV, LV is NL. So that's a level. So that's a number of moles, I guess, in the vapor phase, and then the number of moles in the, which is what I call once again is an amount. Okay. So NV NL over NV over NL is LV over L. So you can think about that as an inversely proportional. That's one way to look at it. But the one that I always like to see is, if you're looking at this length, right? This length is about the other side. How much of the one that you generate on this one. So that's how you use this phase diagram for the level. This is the length, and this length is proportional to the amount of vapor. Right? So this is the proportional one. So this is the length in the liquid phases. They're talking about information on the other side. So one way to also remember this is, if you're here, this is a tie line. Let's say this is a vapor phase, this liquid phase. If your starting composition is right there, you're generating a liquid this much, vapor this much. Right? You're already very close to the vapor, right? So you're not going, yes, you will generate the liquid with this composition. That amount will be like proportional to this length. This is about this length is about the liquid amount. You have that. Okay. If you're right here, and this is the same thing, that at this temperature you will generate the liquid at this composition. The amount of the liquid that you generate is proportional to this. So it's a lot more liquid can be generated compared to the one here that is close to. It's just how you use a lever rule. It is a very simple rule, but it's also can be used quite a bit to calculate. So there are, remember sort of this is the way that how you want to do. Okay, so always when you have a lot of lengths like this means that this one is the amount of vapor is you're going to generate a lot. The other side.